So if we're ready, we'll continue the talk with, so we discussed last time the Fokker-Planck equation, which was, as you remember, important because it was telling us what's the probability that if you have a stochastic process that starts at position, let's say x at time 0, that it switches to a position in the space of y dvy, which means you start at position x, and at time t you want to know what's the probability that your process is going to be located around this point. Right? This is what we said, and we said that this is the probability density function, that is pty condition that you started at x dvy equal this, and we said that the density satisfies the Fokker-Planck equation, which is, you remember, dp dt equal, there was an operator, sigma transpose ij divided by 2 second derivative ij dxi dxj. You remember p sum over I and j. Need to write with a better marker. There is no. Maybe we should take some from the lab. Yeah, maybe it's going to be important. So sum dp dt was equal to this minus the divergence of BIP, where your stochastic equation was x dot equal b of x plus sigma of x multiplied by your Brownian motion. You remember? That's what we discussed last time. The Brownian motion with a drift. B, this is the drift. This is the diffusion tensor. Great. Thanks, user. Thanks. So we said that this, if I know how to solve this equation, I know how to answer this question. Right? Okay, so that's where we stopped. And today I wanted to finish everything last time, but we didn't have time. So now how to solve this equation in general. I'll give you a general way to do it. In particular, it's very hard. But in specific cases, you can expand for specific geometry. In general, it's very hard, but for specific geometry, you can solve this equation. So let me just go into the solution. Why you're interested in this? You're interested in this solution because, for example, you're interested in the diffusion process. You're interested in how long it takes for many molecules to, for example, if you inject molecule you take the example of a dendritic spine, you inject calcium here. Calcium is the main signal messenger in the brain. You put a lot of calcium in here, and you ask how long it takes for calcium to arrive here. So if you are interested in this, for example, at time 0, which is, let's say, during the synaptic input, you have 2 neurons that connect through the synapse. At time t equals 0, calcium goes in with a certain function. This is your initial distribution. Right? And you're interested what is going to be, so this is time, this is the number, and you're interested in what are you seeing here? How long it takes for calcium to arrive from this to that. So you have at time 0 there is nothing, and then there will be something like this, and that's the solution at this position. Let's say let's call it z. So I'm interested at z equals 0. If this is z equals 0, I'm interested in here. What is the distribution of, let's say, the number of particles, the number of calcium ions that arrive at time t, number of calcium ion arriving at time t at the base of the synapse of the spine, the dendritic spine. this is the solution of this problem. How can you get a solution? How can you get a way to get a solution from this? You can just run a Brownian simulation. If I run a Brownian simulation, you go to your computer and you run simulations. And you run many simulations. This would be an approximation for the solution for this probability density function. So alternatively, you can run a Brownian simulation. And usually, most of the time, the way you sample your space of parameters, or you take the solution, you run a Brownian simulation. That's the way to do it. You do it in finance, you do it in biology, especially if you have to explore complex domains. Okay, so how do you write, now we're going to spend a little time on this, how do you write the solution for this equation? Well, let's take, for example, let's specify B is the gradient of the potential, whatever it is. In that case, we'll be interested, so this is called the forward equation. I haven't discussed much this, what is called the backward equation, which is the one that you get as a self-adjoint, the adjoint operator. When you use this, when you remember I had to integrate by parts last time, so the backward operator is obtained simply as dp dt equals, so if I integrate twice by part, it's sigma transpose divided by 2 ddp dxi dxj ij, so this is the matrix you sum, and this is minus the gradient of the potential V multiplied by gradient P. You understand this notation? Gradient P, gradient V, gradient P is the sum, is the scalar product of the coordinate dV dxi multiplied by the coordinate dp dxi. And the sum, if you're in dimension n, 2, 3, or whatever, it's just the summation, right? This is just notation. So how do you write the solution of this equation? Well, usually you expand in what is called eigenvalue and eigenfunction. So this is the formal solution. So the formal solution is expansion in eigenvalue and eigenfunction. So this is, so you know that, so I write the solution. This is ptx to make a jump from y to x. So this is the sum of ck exponential lambda k t multiplied by, let's call it phi n of x, and this depends on y. And you make a summation from 1 to n, where lambda k is the eigen, so this is solution of, so, okay, I'll write it one more time. Okay, I call this, okay, the operator is L tilde of phi n equals lambda n, so minus lambda n, or minus lambda phi n, that's called, this is called the eigenvalue function solution. So, and this operator is simply the sum of d transpose dij divided by 2 ddp dxi dxj minus gradient v, so it's not p, it's phi n, and this is gradient phi n, gradient v, gradient v equals minus lambda n phi n. Okay, and when the the potential, when B is the gradient of a potential, and let's assume that sigma transpose is just the identity matrix with multiplied by, you can have a coefficient D in front, so this is just diffusion coefficient, so this is equivalent to D Laplacian phi r minus gradient phi r gradient V equals minus lambda n phi n. This you can change this, so let me, it's the same in a higher dimension, but to simplify, let's suppose you're in dimension 1. This is D or minus D exponential V divided by D phi prime n, and then you have to do with another differentiation equals to minus lambda n phi n exponential Vd. Do you see this? If I differentiate this is correct? If I differentiate this with respect to V, I got minus D V prime multiplied by phi prime. It's the first derivative. I have to differentiate this. Great. And I have to divide by D. And if I differentiate this one, I have plus exponential V divided by D phi second n. Right? So exponential goes away. Phi prime, this is this term. So I need a minus somewhere. So it should be here. Minus, is this correct? V equals minus gradient plus B gradient, so minus, so this should be with a minus. Right, so if you differentiate this with respect to this term, you have differentiate, you have a minus. So you get exactly this. Is this correct? So here I don't have this plus. And this should be equal to minus lambda n, and exponential goes away. So you agree with this? Can I erase this? Phi n, exponential minus v, so the exponential goes. You agree? Okay. So this is just to say that this can be written this way. And so what you need usually is additional boundary condition. So where the boundary conditions are coming from, I need to make sure that how to do this. Okay. So what are the boundary conditions here? I'm sorry? Yeah, so but we need to impose boundary condition. So if I'm interested in the time a molecule arrives here, what kind of boundary condition should I put here at this specific location? Absorbing, that's right. So which means that phi of n is 0, which is called absorbing boundary condition. And you see that the particle is going to be reflected everywhere else. So then I have to impose d phi n, for example, dn. It's not the same n, but this is normal derivative, which means that the particle cannot escape. So you have d phi dn equals 0, which is called reflecting boundary condition. This is classical. With this leads to what is called the spectrum. The spectrum is the ensemble of eigenvalue, lambda 1, lambda n, that can be discrete and sometimes continuous, but this I'm not going to go into the details. And so that's the solution. And so how do you find the coefficients? Phi n you have to calculate. It doesn't come from the sky. It has to be calculated. And then what is needed is to find the coefficient ck, the coefficient to be calculated. And so usually this comes from the initial conditions where, for example, at time t equals 0, you can say I have nothing or I have something. And so you have a certain distribution at time t equals 0. For example, you can say all particles are located at one point. How do you model this? You can say, for example, at time t equals 0, all the particles are located at the delta Dirac at the point y. And then you have to say, all right, I have to find the solution such that delta Dirac equals ck of y exponential time t equals 0. This is 0, phi k of x, right? This is a delta Dirac, which is this Dirac at point y, otherwise it's 0. And then you need to invert this. And how do you invert this? You use the classical, you multiply everything by left and right by phi k, and then you have to use this condition. Right, suppose I have a function f, just to make sure that this is important. This is the basis of functional calculus. This is your function f of x. So I take f of x, I multiply by phi k of x dx. And so here, to make sure that this is correct, because of this exponential, you have to multiply by exponential, this is a weight function, minus v of x divided by d, and you integrate. So by definition, the eigenvalue, the eigenfunction, they are orthogonals, right? So if they are orthogonals, it means that everything will be 0 except the one for phi k squared exponential v divided by d dx. This is due to the orthogonality conditions that that you have. Right? Oops. So how do you do this? You can, to understand this, for example, you can, if you multiply this by phi n and you integrate, you get, or you take a your function, and phi n, you integrate this, you will get the relation, between lambda n and the phi n. Okay, and so this will give you this is what you do exactly for cosine, and you have a trigonometric series, you expand, you multiply by cosine, and here just you have a weight function because of this term here. And if you divide this by this, so this is not 0 because phi k is not 0, this is positive, so this gives you the coefficient in period. Right? So if you have a delta Dirac, if you replace this by your delta Dirac, it will say that, for example, cky equals phi k of y exponential minus v of y divided by d, and then you have to normalize by this normalization factor phi k squared exponential minus v divided by d. And then you have to replace this in here. This will give you the expansion. Okay, so that's how it is calculated by following the classical expansion in eigenvalues. Why this is important? Because sometimes you don't want to have a sum of exponential. Maybe the first one will be enough. And that's why it's important to understand what are the eigenvalues of your problem. It's usually very hard to calculate. All right, so let's continue. Let's continue with some remarks. If lambda 1, so you have a spectrum. The spectrum starts with, let's say, usually you have 0, the first eigenvalue, the second one, the third one, they are increasing to infinity. And so if the first one is well separated from the second one. Suppose here there is a gap. There is a gap. Usually what happens is that you don't care about the sequence, the rest of the sequence. And so for time sufficiently long, not for time equals 0, because when time equals 0, you see everything can contribute. Because this is time 0, this is 1, so all the theory can contribute. But for time sufficiently long, since you have exponential, and if you are in the condition that lambda 1, lambda 2 is bigger than, let's say, 5 times lambda 1, then you can approximate your process as a constant exponential lambda 1t, and then you don't care about the rest. This is your approximation. And this is quite interesting because this is called the Poissonian approximation. Now you have suddenly a Poisson process because you have an exponential. And so, but this comes to the expense of saying that this is true for time sufficiently large, which has to be defined. And when you have a certain gap between the eigenvalues. Otherwise, you have to use, for example, the sum of two exponentials, which can also be the case, right? Okay, so this is called the Poisson approximation. And so one more thing is that how do you calculate, so this is remark 1, and the remark number 2 is about calculating the mean first passage time. So mean first passage time, how do you connect the mean first passage time? That is the time, you remember, you have here your dendritic spine, you have ions or any messenger of interest, and you're interested how long it takes for this to arrive here. So I want to know, in average, how the geometry, for example, control this process. Well, so suppose you know the probability density function of your process. How do you relate this to the time? So I'm interested in the mean first passage time, that is the mean time to arrive. Let's say to z equals, so this is again z, this is z equals 0, and you're interested, you start at a certain distance L. I know the probability density function to make a jump from here to here for any point y. How do I calculate the time to arrive here?
So for the time, the probability to...
I'm not asking here to look at the transition. I need what is called to calculate the survival. So what is the survival in that case? This is the probability. Okay, let's go slowly. The arrival time, the mean time, is going to be t integration from 0 to infinity of the density distribution of the time, dt. This is the probability that the time equals to. So I know, if I know all the distribution, this is the way I should calculate it. That's the density multiplied by t, that's the mean time tau. That's the classical probability writing of this. Okay, so this is simply, you can look at this as the density, this less than t. Probability equals is a derivative of this density, the cumulative. And so if you integrate by parts, you get that's, okay, you'll do it as an exercise. This is the integration from 0 to infinity of the probability t bigger than t dt. I'll leave you that as an exercise. It's not hard. T, dt prime, if you integrate this by parts, this is t of f minus, if you differentiate t, it's going to give you 1, right? And here you get your f. You'll do it as an exercise. Okay, this is what you get. So this means that this is the so this is called the survival density, the survival probability. This is the probability that at time t you still have a particle in the domain. So now how do you connect to p? how do you connect this to P? So this is called the survival probability. What is it? It's the probability that at time t, you still have the particle inside. Probability that the particle, that's if you're interested in one ions, whatever, the particle is still inside the domain. So how do you connect to P?
1 minus.
Why 1 minus? This is the probability. You are still in the domain. So if you make a transition from this point to that point, oops, it means that if you make a picture, if you take a picture with your camera, you're still inside. You're not outside. So this probability, so suppose you start at position X, condition that you started at X. This is, so I want to make sure that I get all the points inside the domain up to time t. So it means that all transitions are acceptable except if you exit. So if I call this omega the domain, I need to do what? I need to make sure that I am accepting all transition. So then I have to integrate over all possibilities. So this is the integration over omega of probability to make a transition from X to Y. And I have to integrate over dy for all Y in omega. And that's the survival density. So now if I continue this, the mean time is simply the integration from 0 to infinity of the integration over omega of pt, x, and y of dy. Now I can plug this into here and integrate this quantity. So if I'm doing this, what do I get? I get the integration, so I have to sum from 0 to infinity of an exponential. This is 1 over, right? You know this integration from 0 to infinity of exponential lambda t is 1 over lambda, right? So then I have to sum 1 over lambda k, great. Then I have to integrate phi k of x, psi k of y. So if I start at position x, this is where I start, I have to integrate dy. And I have to integrate over omega. So that's in general the mean first passage time if I'm using all eigenvalues. However, if I have only one, I can use the approximation. It's only 1 divided by lambda 1, phi 1, c1, so phi 1 of x, c1 of y dy. So it means that if, for example, you wait for some times, the first eigenvalue gives you the distribution that you have to use to calculate the first passage time, the time it takes to go from here to here. So remember, this is connected here to 1 over the first eigenvalue. That's why it's usually interesting to calculate this. All right? Okay. Enough for the theory. Is that clear what I'm talking about? Or this is classical analysis, which doesn't give you much to solve the problem I've described to you here. Because this, you have to do the calculation. You know, what is the domain, calculate the eigenvalue. It's hard stuff. You have to use some analysis to calculate. But at least you understand, in general, how you do it. Okay, that's it. Now we're ready to move back to neuroscience. I wanted you to understand this because this is fundamental connect probabilities with the solution of some specific, what is called partial differential equation problem associated to diffusion. Okay. Now we're going to need all of this to model spindles. Can I erase? Yeah, it's important to take notes because this is how you remember things. All right, that's it. So now let's go back to neuroscience. I mean, this is cellular neuroscience because many processes in the brain that occur at nano to micrometer level has to do with diffusion, and how geometry controls diffusion is very important. Like dendritic spines, which are part of the synapse, it's called the postsynaptic synapse, is regulated by geometry, and the time calcium is around is quite important. And there are many other quantity of interest, many other messengers. All right, so now we're going to move on to modeling spindles activity with two-dimensional Ornstein-Ulhenbeck process. Ornstein-Ulhenbeck processes. All right. Maybe the word spindle is for you new, so I will explain. Two-dimension, this you understand. Ornstein-Ulhenbeck, I will introduce. All right. So background and definition. So if you plug an electrode, so this is the head of an individual. This is the nose, these are the eyes. You put an electrode here on the temporal or on the frontal cortex. You put an electrode, and what do you see as a function of time? You see a signal which is called the electroencephalogram signal, EEG. You know, you've ever heard of this signal, EEG? I have a signal. If you filter, that's what we'll see. If you filter the signal in the 8 to 12 hertz band, you know what is filtering? You remove the frequency before 8 and after 12. And what do you get when you see the signal? Especially during sleep or anesthesia, you see a sequence of events like this. And so on. This has a name, it is called a spindle. You understand? That's the phenomenology. Great. We're interested in how this spindle can originate from excitation inhibition of a network. So the question is, how can we model? How to model? Model means an approximation, a description according to what we think. That's what is a model, right? A model is nothing but a sort of conceptualization and putting a frame to a phenomenology. So how to model spindle? So model spindle, if you usually what we've tried to do over the centuries is to derive from principle. Newton's law is to derive mechanics from the motion, the law of motion. So here we can say this. I assume that I have excitatory neurons and inhibitory neurons that I'm going to model as one neuron. All excitatory neuron will be one. All inhibitory neuron will be one. Assuming, for example, that when one behaves, they all behave the same. This is called mean field approximation. This is called a mean field approximation. All right. And then we can say that you can have excitatory neurons that are going to excite the inhibitory neuron. The inhibitory neuron are going to inhibit the excitatory neuron. And in addition, we can say, for example, that you can have inhibition or of the inhibitor and inhibition of the excitator. Now, if I use a differential equation to summarize this, I can say x dot x represents, let's say, the inhibitors or the excitator, it doesn't matter. So x is for excitation, y is for inhibition. Maybe I'll change later, depending on what we need. So now I'm interested in writing a course description of this, saying that between time t and t plus delta t, how the level of excitation is changing. Well, the level of excitation is changing because, for example, you have a negative feedback, so it goes back to some equilibrium, and this is, for example, a way to justify this is to say after some time synapses get tired and then they go back to some equilibrium, so if you solve this equation, it's just exponentially decaying. But then you can have a stimulation, for example, a negative stimulation from the inhibitory, so you have minus omega y. And you can have the same for the inhibitor. The inhibitors are going to be inhibited with a lambda y, and plus they are going to be excited, so that's going to become plus by the excitator. And then we are going to add noise. So in the form of 2d1 or 2d w1 dot, 2d w2 dot. So we are back to stochastic equation that we have been discussing now for one class already. This is called, I'm sorry?
The x dot should be plus f lambda x. X dot plus lambda x.
X dot minus lambda x.
It should be plus lambda x, since the excitatory part.
Excitatory gives you
there's a self loop.
Negative.
Right? So
Negative.
excites itself.
No, it inhibits itself. Because
the inhibitor inhibits the excitator.
It's inhibiting. The two are inhibiting because when you fire at high rate,
right,
you become tired, and then you inhibit yourself. That's simplification. All right. So, and plus noise. So I'm asking if this is a description, a correct description. You can argue like Jean. You can say, I'm not satisfied with this. We can put synapses into this. I'm not going to add more description. But from this very coarse model, what do you expect? So how do you study a stochastic differential equation? Okay, suppose you have no noise. What do you get? So now you can look at it in what is called the phase space. Have you ever heard of this, the notion of phase space? Phase space as you are looking at everything in x and y. X and y. Suppose you have no noise. If omega is 0, what do you get? If omega is 0, there's no noise, it's minus lambda x minus lambda y. It's exponentially converging to 0 for both cases. Now if you add omega, what do you get? You get a focus, which means that you have an attractor, assuming lambda is positive, everything is attracted to 0. Good. So this is called a focus. So now I'm adding noise. What do you expect? So if you add a little noise and you are far away, which means x and y are large, what do you see? You see something like this. Right? This is what you do in your computer. The computer will create this kind of behavior. All right, you continue until what?
Escapes.
There's no escape here. until you continue, until you go close to 0. And what happened close to 0?
Never reaches.
What?
Never reaches. So you fluctuate.
You fluctuate. You fluctuate. Which means, what does it mean?
Just noise. The activity is just close by noise.
It's, in principle, you are telling me that if you go close to 0, x and y will be very small.
Yeah.
So at some point, this goes to 0, and then you fluctuate according to this.
Yeah.
So in principle, if you ask your computer to simulate this, at some point you should see just noise. And we will see that this is not the case. Another question is, how do you study this? Right? The intuition would say you have noise here, and we will see that this is not exactly noise, that we have a specific behavior that we would like to study. Okay, so before doing this, let's go a little bit into the notion of how do you study 1D Ornstein-Ulhenbeck processes. Is that clear with you? Or I do a little reminder. A little reminder, maybe that's going to be good. So suppose already what you have seen here is due to dimension 2. There is no circle in dimension 1. So it's already 2 dimensions to get interesting behavior. All right. So now let's go back to Ornstein-Ulhenbeck processes in dimension 1. So which means that they are simply x dot equals minus lambda x plus sigma w dot. Again, it's a stochastic process where 0, I assume lambda is positive, where 0 is an attractor. So if lambda is 0, this is just Brownian. But because of this, it means that you have a tendency, it's not anymore a wandering Brownian motion. Everything will be attracted, in principle, towards 0. So one way to look at it is to study statistical property of the process. What are the statistics? So for the statistics, we need to integrate and look at a realization and average of a realization. So let's integrate this equation. It's very elementary. I just do x dot plus lambda x, which is exponential lambda t x, ddt of this. You agree that I have x dot, I have plus lambda, and I multiply by exponential minus lambda t, and this is equal to this. Right? So then if I just change it in this way, I have ddt of exponential lambda t of x of t equals exponential lambda t sigma w dot of t. Right? And so I can integrate. This is exponential lambda t x of t minus what happened at 0 equals integration from 0 to t of sigma exponential lambda s d omega s. And so x of t is x0 exponential lambda t plus sigma integration from 0 to t of exponential lambda of t minus s. Is this correct? No, it's plus here. Now this is correct. D omega s, right? So suppose you start, this we don't care because for a long time it's going to be 0. Suppose you start at x0 equals 0, it doesn't matter. So this term is 0. So what is the meaning? How do you study this? You look at statistical properties. So what is the expectation of x of t? Expectation is just the average of a realization. So if this is 0, expectation, if you average the Brownian motion is 0. So this is 0. All right. So now what you are interested in here is to calculate what is called the correlation function. So the correlation function, this you should have all seen. Again, I'm going very fast. This should be in your previous classes. So R for the function t of tau is by definition the limit as t goes to infinity of r of x of t and t plus tau, and this is by definition the expectation of x of t, xt plus tau. When you go to the limit, t goes to infinity. So now I can take this, plug into in here, and calculate. You with me? This is the correlation function, and this is what? So this is simply the expectation of what? Of this term. So this is, I mean, this calculation you know how to do, right? Or shall I go slowly over them? Okay, I go slowly. It's integration from 0 to t plus tau of exponential of minus lambda of t minus s. So I call it d omega s. This is for the first one, multiplied by integration from 0 to t of exponential of minus lambda t plus tau minus s d omega s. Right? I just replace this, and this is called t plus tau. I have t plus tau, x of t, and I just calculating, I just replace. That's it. So this is by definition, you can, this is, I have to take the minimum of the two, so this is the infimum of t plus tau and t, which is t. And then exponential lambda t, I have it twice, exponential minus 2, exponential, I don't care about the t, I can put it outside, so it's minus 2 lambda t, right? And I have exponential lambda s from here and from there, so exponential 2 lambda s, and I have an exponential minus lambda 2, exponential minus lambda. So if I make a mistake, you let me know. And this is expectation. As you know, the expectation of this by Ito calculus, this is just ds. Alright, so now this is elementary. This is exponential of 2 lambda t minus 1 divided by 2 lambda, and then I have to multiply by exponential minus 2 lambda t, exponential minus lambda tau. So exponential minus exponential plus, everything goes together and it's simplified to 1, right? And then I'm left with exponential minus 2 lambda t. When t goes to infinity, this goes to 0, and you are left with 1 divided by 2 lambda exponential minus lambda tau. Is this correct? It is. It is, and I have missed sigma squared that is coming from here. Sigma, so there's a sigma squared here, and the sigma squared is coming. So this is what you get for tau positive, because you take the infimum. If tau is negative, you get plus. So in summary, can I erase this? I mean, you follow my, it's elementary calculation. Just this part here, you have to know a bit of the stochastic process, how you integrate this squared. If you don't know this, you have to follow the class. Right here, there is, I've used Ito calculus. Okay, I mean, it's not Ito, it's the definition of the stochastic integral. All right, so when I'm here, so Rx of tau equals exponential minus lambda absolute value of tau sigma squared divided by 2 lambda. And there's one more thing I need. How do you convert correlation function to the power spectrum? Power spectrum does what?
You take square root.
Density function.
No, it's just it's Fourier.
That's right. You go to Fourier. So S x of omega is take the Fourier transform. You take the Fourier transform of R, which is sigma squared divided by 2 lambda integration of the R of exponential minus y tau exponential minus gamma, no, not gamma, lambda absolute value of tau, d tau. And this you'll do at home. This is easy. You split into two. For R positive, absolute value is plus. R negative, it's minus. You integrate, so it will cancel out the imaginary term. And what you get from this is sigma squared divided by a lambda, lambda plus omega squared. This is called a Lorentzian function. Lorentzian. This is the most classical power spectrum that you will encounter in signal processing. So, what do you learn from this? What do you learn? You learn that if you have a process, if you look at the Fourier transform of a Brownian motion, what it is? It's called the white noise. It's one everywhere. While here, if you plot this function is simply, so at 0, this is sigma squared divided by lambda squared, and then it's a Lorentzian. It decays. It decays to 0. It converges to zeros with a speed of omega. Which means that if you look at the Fourier transform of your process, you don't get much of the high frequency. You don't get much of the high frequency. All right. Now, this is what we've done for dimension 1. We need to do the same for dimension 2. To understand what exactly are we talking about in terms of what Jing said is this pure noise? And if not, how can from this system, which is something that is a focus plus some noise, that could lead to something like this, where it comes from? And what are the frequencies here? Do I have a lot of frequency? For example, do I have fast oscillation and slow oscillation mixed together or not? All right, that's the question we are interested in. I'm going to remove dimension 1. Should be clear. All right, so we'll do a break. We'll make a break in 2 minutes. Or maybe this is the right time to make a break. You want to make a break now, so that we take 2 minutes break? Good. Let's make a break now.